Hello and welcome to tutorial number 6. Our topic today is writing chemical formulas for molecular compounds and acids, just some common acids today. Remember before we get started that the notes to accompany each and every tutorial are available online through my website, and I do highly recommend that you have those in front of you as you go through these videos. Okay, so we're going to start with just a little bit of review today from tutorial number 5, where we talked about ionic compounds. Remember that an ionic compound forms when metals, which are on the left side of the periodic table, transfer their valence electrons to nonmetals, which are in the upper right side of the periodic table. Okay, so let's write that down. Ionic compounds form when metals transfer their valence electrons, I'm just going to write E for electrons, to nonmetals. And remember, the overall goal of the atoms is to achieve octet, that stable noble gas electron configuration with a full valence shell of electrons, full with 2 in the S and 6 in the P, for a total of 8, octet. Okay, so I'm going to write here just an arrow, octet. Okay, so your metals are going to lose their valence electrons, the electrons in that outermost energy level, which is never full for those metals, so that they can achieve a full outermost shell. And your nonmetals are going to gain to their outermost energy level, which is never going to be full for those nonmetals unless they're a noble gas, and therefore by gaining electrons and filling up that shell, they can achieve and copy that noble gas electron configuration. They can achieve octet. All right, remember that your metals, because they're losing electrons, they form positively charged particles called cations, and the nonmetals, because they're gaining electrons, they form negatively charged ions called anions. And those oppositely charged ions have a strong force of attraction, a strong electrostatic force of attraction that causes these ionic compounds to be crystalline solids at room temperature pressure and to have very high melting points and boiling points. Okay, so let's take a look at the formation of an ionic compound. Just a real quick review here. Let's do sodium fluoride. Okay, so sodium with its 1 valence electron, remember we can represent that in a Lewis dot symbol with a 1 little dot representing its 1 valence electron. Fluoride is a halogen, a group 7A element, so it's going to have 7 valence electrons. Neither is full with 8, so sodium can achieve octet. I'll just do a little and symbol here. By transferring, let's do this in a different color, transferring its 1 and only valence electron to fluorine, and the result is the formation of a sodium cation. So it lost everything in that outermost energy level, so now you go down 1 energy level, and now that energy level is full. Okay, and fluorine gained, so now it doesn't have 7, it has a total of 8, it has octet. With that comes a 1 minus charge, and remember that we write the formula, it's a 1-to-1 ratio here for the charges to balance out, as overall 0 charge, because the cations and anions will balance each other out. Okay, so the formula for sodium fluoride is written here. Okay, well, molecular compounds form when nonmetals share their valence electrons in order to achieve a total of 8, or octet. Okay, so let's write that down here. Molecular compounds, big focus for today's tutorial. Okay, molecular compounds form when nonmetals typically it's nonmetals, share their valence electrons. Just write E for electrons. And that forms, I'm going to write to form covalent bonds, also known as molecular bonds. So I'll write that in parentheses. Covalent or molecular bonds. And that's how nonmetals can react to achieve octet. Okay, so let's take a look at a very, very simple example of this with the atom or two atoms of hydrogen. Okay. So if you looked at your periodic table, I'll go ahead and hang it up here for a moment. You find that hydrogen is in group 1A and it has just one valence electron. So I'm going to put a little dot here and I'm going to put a little dot here to show each of those hydrogen atoms having one valence electron. I'm going to write a little and symbol there. Okay. So neither of these hydrogen atoms is going to swipe an electron from the other. Okay. Neither is reactive enough to get the other's electron to itself. So the best that they can do is share those two electrons, contribute to the formation of a covalent bond, which we write as a line between the two atoms. So I'm going to put this in a different color here, even than the blue. So I'm writing a little note here. This is to show a covalent bond and one line represents two electrons being shared in a bond. Okay, two electrons being shared. Now, there are double bonds, and that would be two lines here. So that would represent 4 electrons being shared. There are triple bonds, so that would be 3 lines here. That would represent 2, 4, 6 electrons being shared, but we'll get to that in a later tutorial. Okay, so when we write the formula, we're not going to show the covalent bond. We're just going to write H2 to show that there's a molecule where there are 2 hydrogens sharing electrons to achieve their form of octet. Now in this case, hydrogen, by sharing another electron with another hydrogen atom and achieving, let's circle it here in red, 2 electrons. Okay, so that's 2 electrons for this hydrogen, and let's circle it in blue over here for the other hydrogen. That's also 2 electrons shared, but still it counts. For the other hydrogen, well, those 2 electrons in the first energy level, S sublevel, that is a full energy level. Remember that the first energy level only has an S sublevel, so therefore can only accommodate 2 electrons. So remember, helium is the exception to 8. Helium is full with only 2. So in this case, each hydrogen atom is simulating the electron configuration, the stable electron configuration for the noble gas helium. So that's its octet, even though it's really only 2. I hope that makes sense. Okay, so let's write that here. Each hydrogen simulates the stable electron configuration for helium, stable noble gas helium, which is 1s2. Okay, 2 electrons in the first energy level, S sublevel. All right, so I'm going to erase all this, okay, and we're going to go on to, we're on slide 2. We're going to go on to naming the 7 elements that exist as diatomic molecules. Okay. All right, so we just saw two hydrogen atoms forming a covalent bond to form the diatomic molecule for hydrogen, written as H2. Well, it turns out that there are 7 elements that always exist in nature in this diatomic form. Hydrogen is only one of them. The others are fluorine, chlorine, bromine, iodine, oxygen, and nitrogen. Okay, so these are the 7 elements that always exist in nature in this diatomic form. So from now on, if you are faced with writing the formula for one of those 7 elements, you should always write it in the diatomic form. It's especially going to be helpful once we get to writing balanced chemical equations in tutorial number 7. So let's just foreshadow a bit to that right now. Let's say that we were trying to write the reaction to show hydrogen combining with oxygen to form water. Okay. You might be tempted to write it like this. I'm going to use a different color here and put a huge X over that. That is wrong. Even if you balanced it, it would still be wrong because hydrogen does not exist in this single atom form. In nature, it is always diatomic. So it would be H2. Don't forget that little subscript 2. Oxygen is also a diatomic molecule. Always exists in nature in this diatomic form. So anytime we refer to oxygen, we're really from now on referring to it in this diatomic form and forming water, H2O. And I'm going to go ahead and balance this even though we haven't gotten to that yet, just to make it a proper chemical equation, and that's something that we'll cover in tutorial number 7. Okay, so always diatomic from here on. When we refer to one of those 7 elements, we're talking about it in its diatomic form. So let's get on to naming molecular compounds. Unlike ionic compounds, which always have a very distinct ratio of cations to anions, so for sodium chloride it's always 1:1. For calcium sulfide, it's always 1:1. For calcium chloride, it's always 1:2. That ratio of the cations to anions is always going to go back to how those charges balance out. It's always going to be fixed. The molecular compounds can have the nonmetals combining in a variety of different ways to make up a variety of different molecular compounds, each with their own unique, distinct chemical and physical properties. Let me show you what I mean by that. Let's just take nitrogen and oxygen as an example of this. Okay, so nitrogen and oxygen can combine in a 1:1 ratio, just depending on how those valence electrons are oriented and shared. It can combine in a 2:1 ratio, 2 nitrogens to 1 oxygen. It can combine in a 1:2 ratio, 1 nitrogen to 2 oxygens. It can combine in a ratio of 2 nitrogens to 4 oxygens. So all sorts of different ratios with the electrons being shared in different ways to form these different unique chemical compounds. Well, you have to be able to provide a unique name for each of these compounds. You can't call them all by the same name, even though they're all composed of nitrogen and oxygen. They have their own unique and distinct chemical and physical properties, and therefore their own unique names. And that's why with molecular compounds, you're going to have to use a prefix to specify the number of each atom or each element in the compound. Okay, so let me write that up here. So that was just an example. I'll put a little hash mark there. Okay, must use prefixes to specify the number of atoms for each element in a molecular compound. We didn't have to do that for ionic compounds because the ionic compound ratio is dictated by the charge on the cations and the anions, and it can only go together one way. But molecular compounds are different in that those electrons can be shared in a variety of different ways to come up with different formulas, even made out of the same two elements. Okay, so let's look at those prefixes. All right, starting with, and these are written out for you on slide 2, so if you don't want to write them all down, that's okay. They are in the notes. Mono is the prefix for 1. Di is the prefix for 2. Tri is the prefix for 3. Tetra is 4. Penta is 5. Let's go over here. Hexa is 6. Hepta is 7. Octa is 8. Nona is 9. And Deca is 10. Okay, so those are our prefixes. Now let me show you how to use them. So I'm going to erase all this. So I'm going to go in the order of the notes. So let's do formula to name first. So going from a formula to a name. Okay. And we'll go ahead and do the examples in the notes. And 04. Okay, so the rules are already written out for you on slide 3. I'm just going to read through those. I'm not going to write them up here. The first thing you want to do when you are writing the name from a formula for a molecular compound, you'll know it's molecular because it's going to be nonmetals only. Check your periodic table. These are all nonmetals. All nonmetals. Okay, you're going to write the name of the leftmost nonmetal first, dropping the mono prefix if there's only one of them. Okay. Number 2, you're going to write the stem of the rightmost element next. Always use the prefix even if it's only mono, even if there's only one of it. And make sure that you still keep the IDE ending like you did with ionic compounds. So you're going to find out eventually that these electrons aren't really shared evenly, and there is a more ion-like, anion-like element even in molecular compounds. So you keep that IDE ending. And then a few little spelling tips, all right? So if you've got a double vowel, so if you're putting an A, like from tetra, and an O, like from oxide together to get tetraoxide, you're going to drop the A and just call it tetroxide. If you're putting two O's together, like mono with oxide, you're going to drop one O and it's just going to be monoxide. And last but not least, if you're putting two I's together, so if you're doing like tri and iodide, you're going to keep both of the I's. Okay, you're not going to drop either of them. So that's a little hard to remember, but do try to remember the spelling. Most instructors are going to be really particular about that. All right, so let's go ahead and apply those rules to these two problems here. So our first element here is sulfur. There's only one of them, so I'm not going to need a prefix. Okay, so I'm just going to write sulfur here. I don't need to write monosulfur. Never use mono for the first element. Now if this had a 2 here, it would be disulfur. But because it's a 1, we drop the prefix mono. I know, it's annoying. That rule is kind of annoying and students tend to forget it, but try to remember that because it's very important. All right, the next element is fluorine. So we're going to call it fluoride, and there are 6 of them. So it is hexa. Hex is 6. Hexafluoride. Sulfur hexafluoride. The next one, nitrogen, is our first element. There are 2. So we are not going to drop the prefix here. It is dinitrogen. And the second is oxygen. So oxide, there are 4 of them. Tetra is the prefix that we use for 4, so it's going to be tetroxide. That's when that double vowel rule comes into play here. So not tetra, whoops, spell it right, but tetroxide. Okay. All right, let's go on to converting a name to a formula. We'll go ahead and just do it here. Name to a formula. Okay. And I think this is a little bit easier. We'll just do the examples that are right in the notes. Carbon monoxide. And what's the other example? It is silicon tetrachloride. Okay, so these 2 examples. I don't even think we need to go through rules. First thing you're going to see when you look at these names is that the prefixes will already tell you how many of each element there are. So let's just start with carbon. The lack of the prefix should tell you 1. There's just 1 carbon. So when we write the formula, we're not going to write a subscript here, because remember we always drop the 1. It's assumed. You never drop the mono on the second element. So monoxide, notice we didn't keep 2 O's here, we just kept 1, no double vowel there. But the monoxide tells you that there's just 1 oxygen, so we're not going to write a subscript here either. So capital C, capital O, that's it. 1 carbon, 1 oxide. All right, silicon tetrachloride. The lack of a prefix here tells you there's only 1 silicon. And if you don't know the symbols for these elements, use your periodic table. That's what it's for. And tetrachloride, so Cl, how many? Tetra. Tetra means 4. So I'm going to put a little 4 there. So I think that's a lot easier going from the name to the formula. Now really you just need a lot of practice at this point, and I'm going to do a lot more practice in problem set number 6. So make sure to tune into that for more practice going from formulas to names and names to formulas for molecular compounds. And I snuck in some more ionic compounds into that problem set as well, just to make it extra challenging. All right. So let's go ahead and erase here. And before we go on to the next slide, I'm going to just mention 2 common names that are so common that you're pretty much never going to use the chemical names for them. Okay, and that would be water and ammonia. There may be other common names that your instructor wants you to memorize. I think these 2 are probably the most important 2, so I'm only going to write these 2 up here for now. H2O is the formula for water, and NH3 is the formula for ammonia. So don't call this dihydrogen monoxide. Well, you can, and you wouldn't be wrong, but you're most likely going to see it called water 99.9% of the time. And don't call this nitrogen trihydride, just call it ammonia. Okay. All right, so let's go on to slide 4. We're going to talk about ionic versus molecular compounds. Okay, so let's make a chart here of ionic versus molecular compounds. Just write comps for compounds. Okay, so we know that ionic compounds form when metals transfer their valence electrons to the nonmetals, forming cations and anions, which attract strongly via those electrostatic forces of attraction. So let's write those things up here. Just a real quick summary up here. So form from metals reacting with nonmetals. All right, metals and nonmetals. electrons are transferred, which forms cations, which attract positive charge, and anions, negative charge, which attracts strongly. And we're always going to express the ratio of cations to anions in the simplest whole number ratio for a formula unit. Okay, so let's write that here. Express the ratio of cations to anions in the simplest whole number ratio. Okay, so for example, we know that sodium chloride is 1:1, so we're going to write it as NaCl, never Na2Cl2. That's not the simplest whole number ratio. We call this simplest ratio of cations to anions a formula unit. So ionic compounds are made up of formula units. Okay. All right, so let's kind of contrast that then to molecular compounds. Molecular compounds form when nonmetals share their valence electrons in their goal to achieve octet, and in sharing those electrons they form covalent bonds. Okay, so let's write here, form from nonmetals only. And in molecular compounds, electrons are shared to form covalent bonds. Okay. And remember that the number of each atom can vary in a molecular compound, resulting in the formation of different molecular compounds formed from the same elements. Okay, so for example, we use nitrogen and oxygen. We said nitrogen and oxygen can combine in a 1:1 ratio, in a 2:4 ratio. You can have one nitrogen atom covalently bound to 2 oxygens, or 2 nitrogen atoms covalently bound to just 1 oxygen. And each of those compounds is its own unique pure substance with its own unique chemical and physical properties, and therefore its own unique name. Okay, and that's why we had to use the prefixes when naming molecular compounds, because 2 elements can combine in all sorts of different ratios to make up different molecular compounds. Let's write that here. Elements can combine in different ratios to form different molecular compounds. And so your formula for a molecular compound doesn't need to be simplified. If it shows 2 nitrogens with 4 oxygens, that's because there are 2 nitrogen atoms covalently bound to 4 oxygen atoms. All 6 of those atoms are covalently bound together, and you want to reflect that in the formula. So you would never simplify that. If you simplified it to 1 to 2, you would be representing a completely different molecular compound. Okay, so no simplification here. And the formula for the simplest unit of a molecular compound is called a molecule. So whereas your ionic compounds are made up of formula units, which are the simplest whole number ratio of cations to anions, your molecular compounds are composed of molecules, and they're not necessarily in the simplest whole number ratio because molecules show the number of atoms of each element that are covalently bound together. Okay. All right, so let's go on to slide number 5, naming common acids. Okay, an acid is a substance that is capable of donating a hydrogen cation. So I'm just going to write up here, acid is a substance capable of donating hydrogen cation, so an H+. And the chemistry of acids is really a topic for a future tutorial. Today our focus is going to be how to name and write the formulas for some common acids that you're likely to see in an introductory chemistry class. Okay, so typically your acids are always going to have hydrogen written first in the chemical formula. And they're going to be aqueous, meaning dissolved in water, and that's symbolized with an AQ. Okay, so we're going to start with binary acids. Which have just hydrogen and one other type of element. I'll just call it X because I'm trying to be generic here. And there are 4 that you're going to want to know for an introductory chemistry class. So I'm going to write those here. And these are written down in the first table on slide 5. So you don't have to copy all these down if you don't want to. Okay, so when we're naming binary acids, we are always going to start with the hydro prefix, okay, followed by the stem of the other element. So I'll write stem of element. And we're always going to end with the word acid. Oop. Stem of the element with the ic ending, and end with the word acid. Okay? So let's take HF. This is going to be hydro. Fluorine is my other element, so fluoric, IC ending, acid, hydrofluoric acid. HCl is going to be hydrochlor for the stem of the element plus ic, hydrochloric acid. HI is hydroiodic acid. And last but not least, HBr, we have hydrobromic acid. Okay. All right, so those are the 4 binary acids that you are likely to run into in your introductory chemistry class. Now let's go on to the slightly harder part, which are your oxy acids. All right, oxy acids. Kind of as the name implies, your oxy acids, they're going to have hydrogen, of course, because that's part of the definition of an acid, is it has to be an H+ donor. And they're going to have some other element, and they're going to have oxygen. Okay? All right, so I'm going to just go ahead and take a minute to write down all the ones that are on slide 5. And I know I already have the names written down, but I want to show you how I get those names. All right, so never, ever, ever the hydro prefix. Hydro is for the binary acids only. So you're never going to use the hydro prefix for an oxy acid. You're going to start with the stem of the polyatomic ion. Now, if it's a polyatomic ion that ends in ate, A-T-E, like sulfate, then you're going to change that ending to ic. If it's a polyatomic ion that ends in ite, like sulfite, then you're going to change the ending to O-U-S. And always add the word acid. Okay, so let's go through these. So if you are still learning your polyatomic ions, this is going to be really, really challenging. Until you have those polyatomic ions committed to memory, this is going to be maybe something that's a little out of your reach. So I would recommend committing the polyatomic ions to memory first. Focus on that. Once you've got that down, then you can work on these acid names. All right? So again, important to have your polyatomic ions so that you can recognize the sulfate anion here, SO4, 2-. In fact, I think I'll write that here just to help out. I'll write it in parentheses. Okay. Notice that the charge here is always going to tell you the number of hydrogen in the corresponding oxy acid. So again, lots of reasons to know those polyatomic ions. They'll really help you with these formulas and these names. All right, so sulfate becomes sulfur. Because it's sulfate, it becomes sulfuric acid. Okay. Sulfite, SO3 with a 2- charge, becomes sulfurous acid. Nitrate, NO3 with a 1- charge. Remember the 1-, that's going to tell you how many H pluses you need in your acid formula. So it's really helpful to know these polyatomic ions. That's going to become nitric because it's an 8 ending, so nitric acid. Nitrite, NO2 with a 1- charge, is going to give you nitrous acid. Carbonate, CO3 with a 2- charge, is going to give you carbonic acid. Phosphate, PO4 with a 3- charge, that's going to give you phosphoric acid, phosphoric acid. And the last but not least, we have acetate, C2H3O2 with a 1- charge. That's going to give you acetic acid. Okay. All right, so that concludes our tutorial number 6. Please consider tuning in to problem set number 6 so we can work lots of problems together. Thank you.